In this lesson, we're going to add to our list of derivative rules and shortcuts and talk about how we take the derivative of a product of functions and also a quotient of functions. To begin our discussion of how to take the derivative of a product of functions, let's consider this function here as expressed as a product. So we have g of x is 3x plus 4 times 2x plus 1. So in taking a derivative of a product, many people's first intuition might be that you could just take the derivative of each part of the product and then multiply them together. So I'm going to leave this as a question mark equal here. So could we take the derivative of g of x here by just taking the derivative of the first part of that product, 3x plus 4, which would be 3, and then multiplying it by the derivative of the second part of that product, which is 2x plus 1, so that'd be 2. So does the rule work that way? Could we just take the derivative of each part? So to discover what the derivative of g of x is, we could rewrite this in a form that allows us to use some of the shortcuts we've developed so far. So if we rewrote g of x, we could use the distributive property and kind of expand this out. So we have 3x multiplied by 2x, we'd have 6x squared. Then let's see, 3x times 1 would be 3x, 4 times 2x is 8x, 4 times 1 would make 4. So an alternate form for g of x would be 6x squared plus 11x plus 4. So again, another form for that function, and the derivative of g of x through the power rule, sum and difference rule, and so on would just be 12x plus 11. So in comparing that to our first hunch that we might be able to just multiply those two derivatives together, we can see that taking the derivative of a product is not as simple as just multiplying each part of that product together. Like take the derivative of the first part, take the derivative of the second part, and then multiply them together. Product rule is going to be a little bit more involved in that. Fairly simple rule, but not as direct as just doing derivative times derivative. That's not going to work for us. In writing the rule for taking the derivative of a product, I'm going to be using both Leibniz notation and prime notation, just so we can become comfortable seeing things written in the two different notations for derivatives. So let's begin by writing the product rule in a Leibniz notation. So let's take the derivative with respect to x of the product u times v. So in this case, u and v both represent functions of x. We saw that it's not as simple as just doing the derivative of u times the derivative of v, but the good news is it's still a fairly simple rule. We leave the first function alone, which we'll call u, and multiply by the derivative of the second function, so that'd be dv dx. Then add it to the reverse of that, meaning leave the second function alone, v, and multiply by the derivative of the first function, which is du dx. So if you say this in words, it's very easy to remember. It's first times derivative second plus second times derivative first, where first and second are just the two factors in that product. We can also write this using prime notation, so again, just to be comfortable seeing the two different notations, let's write this using f of x times g of x as our product. And if we take the derivative of that product, what this rule says is it's the first function f of x multiplied by the second function's derivative, which would be g prime of x, plus leave the second function alone and multiply by the derivative of the first function, which would be f prime of x in prime notation. So again, first times derivative second plus second times derivative first, probably the easiest way to remember this. Now let's go back and consider that same function we had in the last slide, that product of 3x plus 4 times 2x plus 1. And just confirm that the product rule gets us the same derivative we obtained through expanding and using the power rule, and the derivative we got was 12x plus 11. We just want to confirm that the product rule gets us that exact same derivative. So in setting up the product rule, I'm going to be labeling the two parts of this product with u and v. Nothing special about that. You could use a and b. I might not use f and g in this case since the function is already called g of x, but just give the two functions in this product a label. And the product rule says we're going to do first multiplied by the derivative second, so u v prime plus second times derivative first, v u prime. So we see the four ingredients are the two original functions and their derivatives. One helpful strategy to organize this is to make a little chart of the two functions, and on the same line as the function, put its derivative, and then piece it all together. So the original function u is 3x plus 4, its derivative u prime is just 3, v is 2x plus 1, what's its derivative? Just be simply 2, and we see in the product rule that a function gets multiplied by the other function's derivative. So u gets multiplied by v prime, and v gets multiplied by u prime, and that's how things link together. So in writing the derivative for g prime of x, again, it would be first times derivative second, or 3x plus 4, multiply by the derivative of the other function, which is 2, and then reverse it. Second, which is 2x plus 1, multiply by the derivative of the first function, which is 3. And the little arrows in that chart there sort of show how things link together. Now, at first glance, this looks nothing like the derivative we got through using the power rule on the last slide, but if we distribute the 2 to the first group there, 3x plus 4, distribute the 3 to the 2x plus 1, and simplify, we should get 12x plus 11. So distributing the 2, we have 6x plus 8. Distributing the 3, we have 6x plus 3. And if we combine like terms, we do in fact get 12x plus 11, which confirms that this product rule works. So in the example we just looked at, it might actually be easier to expand it and take the derivative using the power rule the way we originally did. So let's look at an example where the product rule is probably more appropriate. And in this function here, it's probably not going to be that fun to expand this and then apply the power rule to each term. There'd be a lot of simplification in that process. So this is a good example of one that really truly requires the product rule. So again, it's a good habit to give the two parts of this product a label, and I'm going to mix it up and just call them a and b this time. So we'll call the first function here a and the second function b. And again, the ingredients are the two original functions and their derivatives. So let's see. The original function a is just x cubed plus 5x squared minus 8, and what's its derivative? Well, that'd be 3x squared, and we drop the 3 down, drop the 2 down, you get 10x. Derivative of negative a to be 0. And for the function b, we'd have to express root x as x to the 1/2 before we take its derivative using the shortcuts we know. So again, be on the lookout for radicals and also things that could be expressed as negative powers of x and so on. So b, we could leave in the form root x plus 2x, but in taking its derivative, we really want to think of that root x as being x to the 1/2 power. So in taking b's derivative, if we think of root x as x to the 1/2, that 1/2 drops down in front, and we lose a power of x. That'd be, again, 1/2 minus 1 is negative 1/2. Be careful there, and the derivative of plus 2x would be plus 2. So again, as a reminder, what does the product rule say? First function multiplied by the derivative of the second function plus the second function multiplied by the derivative of the first function. So written with a and b here, that'd be a times b prime plus b times a prime. So again, using a chart like this is a good organizational strategy. A gets multiplied by b prime and b gets multiplied by a prime. And we could piece it all together to the derivative. So this is an instance where it's probably just good to write down the derivative and walk away. And there's really no point to simplifying the derivative here. It's mainly just an exercise in using the product rule appropriately. So writing down the derivative, we'd have first function x cubed plus 5x squared minus 8 multiplied by the derivative of the second function, which is 1/2 x to the negative 1/2 plus 2, and then we'll add it to the reverse of that, meaning the second function, so we'll leave it in the form root x plus 2x, and then multiplied by the derivative of the first function, which is 3x squared plus 10x. So again, really no point in expanding this or simplifying this. The point is just to get comfortable using the product rule. So I'm going to box this and then just say write it down and walk away. That is the derivative of f here. Again, really no point in simplifying this one. The next derivative shortcut we'll talk about is what's called the quotient rule. So just like the rule for a product of two functions was not as simple as doing a derivative multiplied by a derivative, the rule for a quotient of two functions is not as simple as just doing a derivative divided by a derivative. Just like the product rule, I'm going to write this in both Leibniz notation and prime notation, and after I've written the rule, please hold off on thinking it's too complicated to memorize until we've written the rule down. There's actually a very nice mnemonic device that can help you remember this, and I actually use that mnemonic device in writing down the quotient rule even to this day. So we're going to begin by writing the derivative with respect to x of the quotient u divided by v. So again, u and v are both functions of x. So in the quotient rule, we do get the structure of a quotient, but we do not get just du dx divided by dv dx. We get the following. We get the denominator multiplied by the derivative of the numerator, so that'd be v times du dx, then minus the numerator times the derivative of the denominator, so u times dv dx, then all divided by the denominator squared, so that'd be v squared. Now let's also write the quotient rule using prime notation. So we'll say f of x divided by g of x. So order does matter in this, since we are using subtraction. You'll also notice there is some similarity to the product rule, meaning one function gets multiplied by the other one's derivative. So again, it's denominator multiplied by the derivative of the numerator, so that'd be g of x times f prime of x in this case, minus the numerator f of x times the derivative of the denominator, which would be g prime of x here, all divided by the denominator squared, which would be g of x quantity squared. So there are some similarities, again, to the product rule in that it's one function multiplied by the other one's derivative, only we've got subtraction this time, and there is some division by that original denominator squared. So one way to remember this is this nice mnemonic device that kind of sounds like you're yodeling. So what I'm about to write is in no way official mathematical notation, but it is a nice way to remember that many calculus students have heard before, and pretty much anybody who's ever taken calculus has probably heard this mnemonic. So I'm going to label the two parts of that quotient as high and low for numerator and denominator. So I'm going to abbreviate that high and low. And I'm going to say this mnemonic a couple of times and then we'll write it out. So if you say the quotient rule using these words high and low, you can make this expression low d high minus high d low over low low. So again, low and high are the two functions. When I say d in that, I mean take a derivative. So let's say it again. Low d high minus high d low over low low for that squared. So again, low d high minus high d low over low low. So definitely say that to yourself a few times. And it does kind of sound like you're yodeling, like yodely hee hoo. So that expression is, I think, silly enough and random enough that you'll probably use it to help you remember the quotient rule. Again, I do use that expression even to this day in taking the derivative of a quotient or in writing the quotient rule down. So one more time, low d high minus high d low over low low. And let's write it out here too. Low d high minus high d low over low low. So again, you can practice your yodeling and say that a few times to yourself, and hopefully that helps you remember the quotient rule. For our next example, we'll look at applying the quotient rule to take a derivative. So this function here definitely has the structure of one that would require the quotient rule, since we have one function of x divided by another function of x. Just like the product rule, it's a good habit to label the two parts of this quotient and then make a little chart that records those two functions and their derivatives, since those are the four ingredients that go into the quotient rule. Now we could label it as u and v, or a and b, or even f and g. However, I think it's a good habit to label them as h and l, meaning high and low. That way you can use that mnemonic of low d high minus high d low over low low. So we'll make a little chart up here for the two original functions, high and low, and their derivatives d high and d low, and just record what we need for taking this derivative. So original numerator is 5x squared. Through the power rule, its derivative is 10x when that 2 drops down. The original denominator is x cubed plus 2x. And again, through the power rule, we drop that 3 down, we get 3x squared, and then plus 2 for its derivative. And the structure of the quotient rule, again, if we think of that mnemonic as low d high minus high d low over low low, or L multiplied by h prime minus h multiplied by L prime over L squared for low low. So in this little chart here, again, one function gets pieced together with the other function's derivative, but order does matter when you're writing down the quotient rule, meaning you'd have to start with low d high, or one expression I've come up with is start low when you're writing down the derivative of a quotient. So in this case, for the derivative of y, we could use y prime. I'm going to use dy dx just to mix it up, so we'll label the derivative as dy dx. And again, we'll piece it together. Low d high would be x cubed plus 2x multiplied by 10x, minus high d low would be 5x squared multiplied by 3x squared plus 2, all over low low, which is just that denominator squared, x cubed plus 2x quantity squared. So we could write this down and walk away at this point, because it is the derivative of y, although it's probably worth it to simplify this. one thing that many students will ask about is this factor of x cubed plus 2x and this factor of x cubed plus 2x here, since we have x cubed plus 2x squared and then an x cubed plus 2x here. They'll ask, well, can I reduce down by a factor of x cubed plus 2x? And in this case, the answer is not necessarily, and probably not, since x cubed plus 2x is not a common factor to both terms in the numerator. Notice there's this subtraction here, so that's not an allowable simplification. What we can do is probably expand things in the numerator and collect like terms. We might be able to make the numerator look a little bit nicer and a little bit more simple. It's probably worth it to do that here, since likely a multiple choice question will do that. It's probably not worth it. In fact, very rarely is it worth it to expand out this denominator. We typically always leave that in that form, unless we notice something else down the line. So again, to write this in a more simplified form, we will kind of clean up the numerator a little bit. So in the first group there, if we distribute the 10x, we get 10x to the fourth plus 10x times 2x would make 20x squared. Now be careful of this subtraction here. We actually have to think of this as distributing negative 5x squared to both those terms, so be careful to not make a minor sign error in doing this. Kind of take your time. So negative 5x squared times 3x squared would make negative 15x to the fourth. And be careful with this one. Negative 5x squared times positive 2 would make negative 10x squared. So again, be cautious of that. And again, we'll leave it all over x cubed plus 2x quantity squared. And in the process of expanding, I do recognize a couple of like terms there we could combine together. 10x to the fourth minus 15x to the fourth would make negative 5x to the fourth. And then 20x squared minus 10x squared would make plus 10x squared. And that's still all over x cubed plus 2x quantity squared. And that's all well and good. That would actually kind of work as a nice simple form for dy dx. I think other things you might be able to do to rewrite this is I recognize there's a common factor of either 5x squared or negative 5x squared in the numerator, but I don't think we can really go much further than that. Could be worth it to do that depending on what else the problem involves. So maybe just to show, you could take out a common factor in the numerator if you wanted to. So maybe we would write dy dx. If we took out, let's say, a common factor of negative 5x squared in the numerator, we'd be left with, that would leave us with x squared minus 2, and then still all over x cubed plus 2x quantity squared. So that could be another form you'd see the derivative written in. For our last example, it looks like we have another function that's perfectly set up for the quotient rule, since again we have one function of x divided by another function of x. However, it's important to always consider if there are ways we could change the form of a function that might help us to save a little bit of work and perhaps even avoid something like the product rule or quotient rule. One thing to recognize about this function h of x here is that there's a common factor of x in the numerator that might help us simplify with that x that's in the denominator. So let's change the form of h of x and see if we can determine its derivative through an easier process than using the quotient rule. Again, this isn't always possible for every function, but this is an example of one where changing the form might be to our advantage. So let's rewrite h of x. Granted, there is a common factor of 5x in the numerator, but it's really that common factor of x that I think is going to help us. We're just going to take out an x to start with. And we'd be left with 10x squared minus 15, and that's divided by x still. So now we can simplify out that common factor of x. X divided by x makes 1, and we're left with the simplified function 10x squared minus 15. Now we have to be careful because at first glance it might look like we're left with a function whose domain is all real numbers, but that original function did not have a domain of all real numbers. In fact, there's a domain restriction when x is 0, so we would want to qualify that h of x is equivalent to 10x squared minus 15, provided x is not 0. He would have to make that qualification. And that would also apply to its derivative as well. So one thing to realize is, in changing the form here, we've actually changed this from a quotient rule problem to a nice simple little power rule problem. If we take the derivative of h of x here, we would just get 20x, and then the derivative of negative 15 is 0. And again, throw in the qualification that x cannot be 0. That makes this much, much easier to work out. We don't have to go through using the quotient rule and then simplifying to end up with this function for the derivative of 20x. So that's something to be on the lookout for, especially in a multiple choice question. You might not at first to realize that there are alternate forms you can put a function in that might save you a lot of work, especially if you're looking for a nice simplified answer in something like a multiple choice question. So again, important moral in this one, always consider if there are other forms you can put a function in that might make things a little bit easier before you take its derivative. To end this lesson, here are 3 practice questions on using the product rule and the quotient rule. You also want to consider if there are alternate forms you might need to write certain terms in, or even the entire function in, that can help you solve the problem a little bit easier.